kind of sets it up. I don't know what. I don't know what to say.
Right.
Wait.
We don't make this stuff up.
Hello?
It's real.
Oh, sorry. Sorry, everything. Wait, why is everything freezing?
No, it's Skype.
Oh, so I shouldn't start flailing around like that?
Oh.
Hey, Matt, do you know what time it is?
I think it's cloud time. That's what I think it is.
I think it's time for another episode of Cloud Simplified.
That's right.
We're going to bring together some experts to you, the audience, to try to distill down complex topics of Azure and highlight how some of our customers that we're engaged in working with are using it. So first off, I got a comment, Matthew. You have an awesome looking shirt there. I see you're representing. Yeah,
that's right. Got to represent my cloud. I love my cloud.
So I also want to thank all the viewers. We have 150 or so subscribers.
Yep.
Great to see things get off to a good start.
I guess we're doing something right? So
that's right. Yeah. So I want to pose a challenge to the viewers. We'll in the comment section on our YouTube channel, if we get some suggestions and some of the things that you would like to see, we'll send out some Cloud Simplified stickers. So
heck yeah, that's right. Yeah. Let's hear from people.
Yeah,
be good to hear from them.
All right, and as always, we'll have show notes and other blog posts and so forth on cloudsimplified.io. So definitely be sure to check that out. And today we have with us a special guest, Laura, who is a data scientist / data solution architect that we're going to be bringing in and walk through a little bit on machine learning and some facets of some of our data technologies that seem kind of daunting and complex when you look at them at first, but she's going to help distill them down and make them simple.
So you're telling me she's the smart person, right? That's good.
That's right. Yeah,
like
you and I are here for the looks.
Yeah. Well, you mean I'm here for the looks? She's here for the smart people. I got you. Good.
All right. So Laura, how are you doing today?
I am doing awesome. How are you guys?
Oh, we're doing well.
Oh, that's excellent. Look, we're both in red.
That's right. Smart people.
I'm the odd guy.
I know. We should have sent you the memo.
So Laura, why don't you tell me a little bit about what you do for our customers?
So a lot of times I get brought in when the words machine learning come up, and I think part of the challenge is just helping the team and others understand what is machine learning. And it is this very popular used term today and thrown around the dinner table, at least at my dinner table. And so this session will hopefully clarify using a lot of layman's terms and comics what machine learning is and how you could potentially use it in your different accounts like I do.
Great. Okay. So do machines really learn? Because I think that's one of the things I want to learn today is it possible? I mean, are we talking like artificial intelligence, Armageddon type of machine learning?
Well, if you think about you learning and your brain is a machine. So yes, okay. You can use that analogy. And yes, very much so. The machine does learn. And we will get that in today's presentation.
Look forward to it.
All right, Laura. So why don't you walk through a little bit what you have to show us today?
Sure. I'm going to take you through a brief history of machine learning. And so a lot of what we're going to be talking today really centers around, I think, this quote, which is fantastic. So I wanted to ask you guys, do you know who said this quote? It's tough to make predictions, especially about the future.
Well, you said I was going to learn today, and my brain was like a machine, so hopefully you're going to tell me the answer?
The answer is it's Yogi Berra.
Oh, there you go.
And so if you think about, that Moneyball baseball analogy where you're using machine learning to predict out who are the cheapest players that you could potentially attract to your team while still achieving a high, runs per whatever. I'm not a baseball person, but you get the point. So in football, you want to, the Cleveland Browns this year did a very similar thing where they tried to apply the Moneyball algorithm to picking who they should go ahead and draft, and it really didn't work. And that's a really important theme to this presentation is that machine learning doesn't solve everything, and especially if you don't apply it correctly.
Yeah, that's a great point.
That's cool. Yeah, I was going to say Doc from Back to the Future, but
he was like my hero as a kid. Like I got a flux capacitor, which is really something my family made out of some PVC piping, but it was awesome.
I want to borrow that for a party sometime, just so you know.
Okay.
All right.
And so oftentimes, if people don't realize how much machine learning actually infuses everything, they think about the newer AI systems like the facial recognition, but even down to when you're watching your daily news commute, how long is traffic going to take? What does the weather look like? All of those things are actually various flavors of machine learning, or even your Google search results. So, we know, Big Brother Google is watching, and that's how Google knows to surface up certain ads, and all of that is machine learned based. And so it's everywhere. And so it would be helpful for everyone to understand what it actually is. And so there's 3 types of machine learning. There is supervised learning, there's unsupervised learning, and there's reinforcement learning. Of these 3, do you know what any of them actually are?
No, I usually think I need to be supervised at all times, so maybe that's my kind of where I need to be, supervised learning.
That's a very fair assumption. So supervised learning is the most common practice of what people are used to when they say machine learning. You can see on the left side here what is considered a classification model. This is a type of supervised learning. So by looking at the pictures, you would know right away, is this a hot dog? Is it not a hot dog? You might want to eat your shoe on a bun, but, not unless you have enough relish, maybe.
I prefer hot mustard, but okay, I get your point.
And then on the opposite side, probably the most popular use of machine learning is regression. So, I would love to say I make $100 million as I negotiated my salary at Microsoft, but all of that is, Microsoft determining or using a type of forecasting to say, how much do I need to offer this person to bring them into my company? Or what is my sales forecast? How much do I need to earn to be able to be net positive when I close the books? So these are the 2 most popular types of machine learning today, supervised learning. And yes, we should supervise you as well.
Yeah, appreciate that. I'm glad you agree.
Now, unsupervised learning is the type of learning where we don't know anything about it. So in this instance, we don't know it's a hot dog. We don't know if it's a shoe. We don't know anything about the data. And this is the big differentiating point between these 2 types of machine learning. Whereas the first type, supervised, we knew what labels to assign to those items. This is a hot dog, this is a shoe. In this instance, unsupervised learning is where the machine actually creates those labels for you. So it buckets together things like weight and height. You can imagine along the x-axis or the horizontal axis, if that was your weight, and along the y-axis or the vertical axis is your height, you could then see the corresponding relationship between, is it true that the taller you are, the bigger you are? And so by having those buckets put together, the machine can then start to assign a classification or cluster name or labels to those different data points. So the big difference is on one side we know the label, on the other side we do not.
So
interesting.
So this is so like Windows Hello would be an example of supervised learning where we've trained it with numerous models, different lighting and so forth for my image unlock my computer. Whereas unsupervised learning, if I had manufacturing data in a automotive plant as an example with sensors from different types of machinery, and I wanted to create. I didn't really know what correlation existed between, vibration or temperature or, humidity. I didn't know what factors really, affect the quality of my part. And you're saying unsupervised learning would be an example where that data could be analyzed to try to find patterns that maybe
Absolutely.
Okay.
Yeah, no, that's a great example where oftentimes our customers will ask us to come in and talk to them about, I've got all of these different columns or attributes or features. They use a ton of different names, but it's essentially data that describes their data. So things like, I need to know all of, if we're talking about travel data, you want to know where are you going? What are the dates? What are the days of the week? What are the times? If you wanted to predict out things like delays, or in your instance of manufacturing, if they want to reduce the cost of having errors or quality issues in their manufacturing process, they then want to know what are all the significant actions or features that impact causing errors in my manufacturing process. And so when you don't actually know what could be the driver of those issues in your process, that's where unsupervised learning can then say, these 5 features are the most correlated. They're going to move that needle the most. And therefore, that's important because if you think about the cost, computationally, every time you want to do any type of analysis, whether they're machine learning or not, the more you can hone down these different types of attributes, the better your analysis is going to be overall. And that's key in machine learning, is that every time you run through what we call this parameter tuning and you do dimensional reduction to just those core dimensions that matter, you get better and more accurate model results. So that was a very good analogy on the manufacturing side.
Okay.
All right, and the last one, if you know anything about Pavlov and his dogs, is very much what you might think reinforcement learning is. We've been reinforced our entire lives since we were born. Our parents reinforced us with positive reinforcements, and when we did something wrong, potentially negative reinforcements. And then there's also the concept of punishment, and that same concept holds true in reinforcement learning. And so I think these are, really funny comics to really, talk about the reinforcement learning concept, where, the more that you go through and you collect answers, and if the answers are wrong, they just say, just keep stirring it until you find the right answer, much like stirring that pot. And so that's very true in machine learning. It could be super frustrating to keep training and training, but the reality is if you don't do that, you're never going to actually find that right answer.
So and the word learning is used a lot in these machine-based algorithms, and fundamentally it's just a big statistical model or linear algebra. Is that not the case?
It is just a giant statistical model, but there is a difference between machine learning and statistics. And while machine learning encompasses statistics, statistics doesn't necessarily encompass machine learning. So things like, for example, correlation is a great example. Looking at, what X inputs or what values or what dimensions are correlated to others, that is a statistical practice that can help us understand our data, definitely. But in machine learning, as you're going through that pre-processing, those early steps before you ever get to the machine learning algorithm, it's still helpful to run through a series of those activities to better understand your data. So remember, statistics is not machine learning, but machine learning always involves statistics. It's just another deeper lever.
I thought we got away from statistics back in high school. I guess not.
No, and I know I love those classes. But most people's eyes glaze over when I start talking about this, like, I don't really care what you're saying.
Yeah, I'll wipe the glaze away from my eye just right now. So.
Yes, exactly. All right, so if you were to look at this comic, do you know, of those three that we just went through, which type of machine learning is represented here?
Do we going to get Jeopardy music along with this?
Internet history. So is this supervised, where we have some model that's already some history of data? Because one of the first two.
Very good. It is one of the first two, and it actually could be either or, because the question would be, did we already know what that internet history was to know that you might be dumb enough to enjoy extreme sports, or did the model tell us that? I love extreme sports. I guess that makes me dumb. But
well, if the internet's trying to kill me, then I don't want any part of it.
And so part of building these models, and this is something that I get asked about a lot, is, where do I begin? And so thinking about what we've just talked about into business cases, when you walk into a customer and they know very little about their data, or they have a gut feeling about their data, always be wary. Even if they're the best subject matter experts, they will definitely come in handy as we retrain and hone these models, they still have preconceived assumptions. So, you go into a telco provider and they will have preconceived notions about what's causing churn. Or you go into a retailer and they will have preconceived notions about what's causing, their revenue shifts via seasonality. Everybody's got those preconceived notions the longer they're in industry. But the reality is that you should take a really unsupervised look at that data first before starting to apply those labels, because you can either validate it, good job, you were exactly right, or you can find out that no, actually, you've been building your business based on these drivers that aren't 100% moving the needle. They might be significant, but they might actually be less significant than others. And
that's a really good point. What I've tended to notice is that data tends to be very siloed in the customers I've gone into. That you might have finance data. Finance is going to know and understand that very well. You're going to have retail data. Using your cell phone analogy, how many transactions occurred, where, what part of the, what geographies the particular retailer is selling more more phones? Is it in accordance with a particular sales or promotion they have in a geography or set of zip codes? But and then you might have manufacturing data on when new models are coming out and so forth, and you have all these different distinct units of data that typically is related somehow, but it's not often, the customers aren't often aware that they're related. So, do you see that sort of thing?
Oh, absolutely, and see it all the time. One of the interesting examples from a past life working with the largest European telco provider was that they were of the mindset, much like their U.S. Subsidiaries, that these certain set of factors caused churn in the telco industry. And as we all know, the latest and greatest plan or phone, can trigger somebody to change from one of the big providers to another. And what we actually found in their data especially was that it was actually bringing in third-party information like events, so things like back to school, the holidays, those types of things, was actually a more significant contributor to when people change plans. And that was very puzzling until we understood that European telco providers still have many pay-as-you-go customers. It's probably more popular than the plan customer. And so you think about pay-as-you-go and it's like, oh, of course, you're going to school, your parents get you a phone, it's the holidays. And all they do is end up pulling out their SIM cards and sharing those, and that's how they operate differently than us. But again, without that data, we were built off of these assumptions, and that's what brings us to this building the model slide.
Well, thanks, Laura. So why don't you walk us through this a little bit? On how you go about actually establishing and building a model, because I know that this is where I tend to get confused when I start opening up the machine learning workspace and actually start trying to drill into taking a data set and distilling it or breaking it down. What's involved exactly in working through that?
Sure. So one of the first things I do when I'm looking at this is the why column that you see there, the label, you should have one very good question that they've asked you that you are trying to solve for. For example, what are my sales going to be in Q4? How likely is a high value customer to churn in Q4? It doesn't always need to be temporal, meaning time based. It could just be who are my high value customers. But in any event, you want to have a very crisp, clearly defined why label. You want that individual column that you're solving for. Every new variable or question that they ask, if they say, I want to know what my sales are in Q4, and it would be helpful to understand, what my margin impact will be, that's then another why. That's a whole other than model that needs to be looked at for that. So you need to make sure that they keep it very crisp in terms of, the why, what are you predicting, what are you calculating for. That's why you see in this diagram just one column. When it comes to the features that could define or that could be the predictors of that why, that's where you can have one to n, one to many of the dimensions. And so with each one of what you see here in these examples, think of them like columns in the database. So you might have geography. You might have that geography hierarchically where you have, country, state, city, zip code, region, whatever it might be. But each one of those represents one of those columns. So I always like to think of it in a business intelligence sense because a lot of people understand, that traditional star schema model, which is you have a fact table which contains your numeric measurements, and around it you have these spokes which represent the dimension tables or the dim tables, and that describes it. And that's very similar to what you see here. The reason, and so you think of those columnarly. When you look at the rows, and you might be asking yourself, well, why are there so many different rows that go along with it? That aren't the rows of values that are in there. Those are actually the number of times you train. And so at its basis, you want to have that crisp why that you're predicting for. Let's just put that in column A in our virtual spreadsheet I'm building with my hands. And then everything else that follows it should be a feature. That's sort of the core of how you start.
Okay, that's interesting. So some customers that I've spoken to, they hear the word machine learning, and I can just throw a bunch of stuff at it, and it's just going to spit out a bunch of results. And what I think is important that you highlighted that you need to have some outcome or result that you're actually trying to drive towards to actually build a model, and then ask questions of your data from that.
Absolutely.
Yeah. Okay.
And it's quite amazing how probably a good 80% of the time when I'm brought in, that why, that question they're trying to answer hasn't been answered yet. Like you said, they want us to come in to talk about machine learning to solve, operations. You can't solve operations with machine learning. I mean, you can, but there's a whole host of other things that go in there. And so one of the things I learned when I was going through Six Sigma Black Belt training a long time ago was to always ask the 5 whys. So if you ask somebody why 5 times, you can usually get down to the root cause or the answer that is what you're actually looking for. So someone says, I want to solve operations. Why? Because currently we're wasting a lot, currently there's a lot of inefficiency. Why? Well, currently our staffing model is broken. Why? Well, currently we're not using a system of record to do it and it's all manual. Well, why? We don't have one in place, and so we need one. So by the time you get to the bottom of it, you understand they are doing manual staffing augmentation models, and so your why would then become, what percentage of headcount do I need on staff during X time period, or what do the shifts need to look like in terms of staffing in order to achieve 100% efficiency. That's how you get from I need to solve my operations into more of a predictable why that you can answer for, is asking those 5 whys to get down to the bottom of the question.
That's
okay.
pretty
Yeah,
cool.
really
I've got a question.
Yeah.
So if I'm working and I don't know my why, let's say back in a previous life, I came from a research company and we're trying to take multiple data sets. One statistical, one is very entomological, if I even said that right, anatomy, and then one that's based on standard treatment paths in the world of cancer, right? But we wanted to answer the question, if I knew your genetic makeup and I knew about the right treatment, would I be able to change your outcome or the efficacy of that treatment? So, I understand if we come in with a great question, we have the answer so that we know that we're in the right space. But what if now I'm trying to solve the questions that I really don't know, or I certainly don't know the answer to? How do I get to there?
So that's another layer of complexity of the models we've looked at so far. So let's just take logistic regression, which falls in the type of the supervised learning regression type. Well, you then have, in the example you're giving, it's more of a blown out version of that, where you're going to have a whole multi-factorial, meaning you have many factors that could impact the other. And so, yes, to determine an outcome, if the outcome is Y, whatever that outcome might be, maybe it's reduced mortality, maybe it's, I don't know, increased longevity, something along those lines. You'd still want to know a more crisp definition of what the outcome is they're measuring. But once you have that, you'd have to apply more of what's called a neural network. And what a neural network is that sort of blown out regression where all of those different multi-factors and features can be measured together and then spit out into many different layers to get down to that bottom answer, because you have just so many things that could impact the other that you don't know. Is it environmental? Is it because of the anatomy? Is it because of all of these? And then within each of those, there are many other levels. So because you have many levels, it's an onion. And to answer that onion, you need to go much, much more advanced than what we're showing here today. And that would be where you'd apply more of a neural network. And funnily that you asked that question, I actually have a 15-minute neural presentation for our lightning hypo talks that are coming up very soon. So do you guys know why we split our data into training set and test set?
Is this a quiz? I'm not sure.
It is. I know. Friday afternoon quiz.
So is this so test set in my assumptions would be a known a set of data that we can actually validate whether or not our model is accurate, kind of walking through the slide trying to figure out if that's...
That is very good powers of deduction reading that, but no, it's very accurate, and pun intended. So one of the things that it can plague a data scientist is the term overfitting. And what overfitting means is basically if we were to take that full training set, 100% of our training data, and run it through these models, well, we would never know if that was a good model or if we had overfit it to the data because we have nothing to test it against. So the test data gives us that ability to test against our training data to know whether the machine did better than we would if we were to predict it ourselves. I mean, that is the goal of all machine learning. If you think about, flipping a coin, as a person, we have a 50-50 odds of landing heads or tails. Well, if a machine is going to be built and algorithms are going to be used to predict something better than 50%, well, I'm sorry, if a machine is going to be used to predict something, it needs to be better than 50%. Otherwise, the human would just do it, and it would suffice. And so the whole goal of having training and test data is to first not overfit your model with that full data set, and second, make sure that the machine is actually predicting better than you could, or better than the data could on its own as it is today. And that's really why we break into training set and test set, is to be able to measure that accuracy or measure that precision in order to get a better prediction.
So what would a customer normally do in this case? So let's say that I've got 10 years of sales, and using your cell phone example, 10 years of sales and transactional data and from stores and so forth. So I have that I'm using to train, and then what do I test that with? Is that test set a subset of what I've trained it with, or is it?
It's the raw data. It's from the very first thing in your full data set. Once you've done, so there's some pre-processing steps that aren't represented on this slide in between full data set and training set or test set. And in that pre-processing, you want to do things like fill in the zeros, make sure you don't have any dirty data, pretty much that standard ELT model where you want to get it loaded somewhere and then you need to transform it just to make sure it's clean. But once it's clean and once you've filled in gaps, you want to immediately split it, whether it's an 80% goes to training, 20% goes to test, whether it's 70-30. You want to then split it right after you cleanse it so that you have that pure, unadulterated data to test your training set against.
Okay, that makes sense. So thinking about this in terms of Azure, the full data set could come from all sorts of things, whether it be comma-separated file, other databases, and we could ingest that into something like an Azure data lake.
Absolutely.
And we have some things in the middle that we can actually use to do that massaging. Azure Data Factory is a component I know that we can, one of many choices that exist. And is that typically we kind of see customers making use of all those individual components to kind of break things down and ultimately get that training set of data?
Yes, so definitely. And at the end of this, there's just a really high-level Azure ML slide, but Data Factory is very effective for orchestrating the movement, because if you notice on the training set line and the test set, you want to break those into pipelines and using the Data Factory analogy. So you have your training pipeline, which is going to take all those features and it's going to munge them and look at which ones are statistically the most valid, the most correlative, whatever it is that we're running. And the output of all that training is going to be your model. And once you have that model, again, a second pipeline in Data Factory would be to then have the test set of data, that unadulterated 30 or 20%, that you can then compare to that model for accuracy. For the prediction accuracy. And so Data Factory would handle all of that throughout, moving pieces of it in and out of whatever storage that you're wanting to do. Often I use Blob because it was the first supported sync or data source. But now with Data Lake, of course, you could use Data Lake storage. You could also use any of the relational. You could even use Cosmos DB with the Spark connector. I mean, there's a whole host of things in Azure you could use.
Okay, cool. All right. So what else do you have to show us?
So then, moving forward, and this is going back to my coin flip, this is the most important thing that I think people cut out when they're going through this. They race into, whether they're using Machine Learning Studio or Workbench, they race to getting into starting to build the model. But you always want to have that baseline first. And this is basically a dummy model. And sometimes this could be, if it's a finance example and they want to do sales forecasting, this could be the spreadsheet that they're using today. That becomes your dummy model. Because you want something to compare your end results to, other than the test data that may validate and say, yes, this is a good model. But still, you want something else that they're doing today manually that you could use as that dummy model to compare to. And that's called the baseline model. That is very important because people will have many times customers will give us what they're doing today, but people don't realize that artifact needs to be part of this whole process so that when you have your end results, you could then say, for the cell phone example, we were able to predict churn of your high value customers of this. Your marketing team said churn would be that. And now we can see what the difference is between the two. And if there's a huge gap, then there's things you might want to hone in your model. Your model may still need finer tuning. Without that baseline model, how do you know if it's good enough? You wouldn't.
So what's the time involved in for this type of process? And you say you've got some very important steps that you have to take. The customers, oftentimes, like you said, race to the end, or they try to, answer this question because I think there's a lot of, we want to show value for the work that we're putting into, especially a very cool technology like this. So help me understand kind of a broad timeline from start to finish. What do you see, or what do you think customers should expect?
So I would say coming from our end is always bring in a data scientist or machine learning expert with somebody who can help with the data. And why this is important is, there's an example with one of our customers where we only had 2 weeks and they wanted a full blown out recommender system. And in that, that's a very tight time frame for something like this. But by splitting it into 2 roles, what we were able to do is I was able to focus on getting the algorithm ready to consume the data while my partner was able to use, in this instance, data lake analytics to push through various different SQL scripts and pump out queries that I could consume directly without myself having to do the pre-processing and the query summarization. So it was very, very time reducing, very helpful.
Very good. Okay. So I think I picked up something too is, hey, Ryan, I think there's a swarm effect that as it comes into play, right? So that's great.
And sometimes, you're going to get brought in and, if you don't have that, then these models can take, in upwards of, 3 to 4 weeks, depending on the complexity of the model. So I would always recommend the swarm approach. It's very easy to divide responsibilities and tasks between having more of the data side person and then having the machine learning person. And then you can come together at the end. Very, very much speed up. All right. And so how do we know once we've, run through this whole, we've gotten the data set, we've gotten our baseline of what they're doing today manually, we've split it into training, we've tested it, we have a fairly high accuracy rate. Do we know whether that accuracy rate of our prediction, though, is good or bad? If I told you that I had a model that could predict brain cancer within a 99% accuracy, is that good or bad?
Is that like a trick question?
It actually is.
I might be scared of the 1% time. I don't know. Maybe that's the answer.
No, that's very astute, because the first thing I would think is I'm a skeptic by heart anyway. I would want to know more about that. I would also want to know how precise that is. Just because I can throw a dart and hit the bullseye with 99% accuracy, that doesn't mean I can repeat it over and over and over again. Is this a one-time thing, or can I do it over and over? And that's the difference between accuracy and precision. Precision, giving you the ability to repeat that accurate result, is a very important factor. And this is why in the model evaluation is such a critical step, because the metrics that come out of evaluation will not just only tell you how good your model is and how well it fits the data, but it'll also tell you, when you look at this and implementing it overall in the real world, how well it will apply to those real world data situations, like your example with the complexity of in the genomics world. You can't just say you're predicting brain cancer with 99% accuracy without then understanding a whole host of other factors that go along with that. And that's why model evaluation is never something to skimp on. It's a very important step of the process.
Hey, guess what, Ryan? I'm not skipping on a model evaluation, especially in brain cancer.
I'm giving you the teacher finger with that, so don't do it.
Yes, you did. Yes, you did.
And so these are some of the classic, what you will see if you're using, whether it's Azure Machine Learning Studio or Workbench, these are the type of metrics that will come out in terms of the evaluation step. So we've already talked about really a lot of the classification side in terms of accuracy. Oftentimes it's visualized as something called the area under the curve or ROC curve, and all that means is how much of this area is captured by my new classification. So if I say that's a hot dog, is that encompassing all of the different samples that I have accurately, or am I missing some, or am I capturing some other things that maybe look like a hot dog, like a submarine? Who knows? That's where it's important to understand this area of under the curve chart that, Azure does a great job of pushing forth for us, so we don't have to think about it. It's already part of the available set of metrics and visuals that we have. Similarly, on the regression side, I often hear people talking about this R squared, the third one you see on that list. R squared is high. That means it's very correlative, and that's true. R squared is a representation of how strong these drivers or features correlate to that Y value we're looking to predict. But that is not the only measure. That just tells us about our feature set in the data, or our X values. But how good does the model do at predicting the forecast? That's a whole other can of worms in the evaluation side. That's where this RMSE or MAE come in, which just basically means the root mean squared error. It's how great of an error are you at predicting this? And this is a totally relative number. So again, I've heard people mistakenly say you always want an RMSE that's very, very small. Well, if we're talking about, the number of miles on a car that we want to predict in the longevity of a car, and someone says to me that, they can predict the life of the car within 2,000 miles, I'll say that's pretty good. But if someone tells me that they're going to predict, how long I'm going to live within, 2,000 years, we know that scale's totally off. And that's why understanding RMSE, it's very relative to the data that we're working with.
That's some great points.
So with those types of regressions, now what do we have to make that a little bit easier to comprehend or to know if you're on the right track? Do we have, is there something that can help customers with that? Or
so we do push forth the metrics for you. So we tell you what they are. And then in terms of visualizing it, we have very easy graphical capabilities to put those mean squared errors on a chart. And why that's important is, let's think about your standard sales forecast. You have your chart and you have your line that's predicting your sales forecast. Well, once you start placing... Hopefully going up. Yes, we don't want to see it going down. That's not good. But hopefully when you apply the errors against the predicted, dots on there, and you look at how well you did, you want to see those dots as close to zero as possible, or as close to the line, because that means you had very low error in predicting them. So I always recommend people to take, the values that we show forth in Azure and just plot them. It's a very simple call that you can include just so you can graphically see them against your forecast. It's so much easier to grok something when you see it visually than when you have to just look at a numeric, in my personal opinion.
I have a prediction.
What's your prediction?
Do you want to hear my prediction?
I do.
This show's going to rock. This has been great. So I really appreciate it.
And just on this last slide here on the confusion matrix, and this goes back to the cancer example and or the genomics example. Part of measuring or looking at the evaluation when we are applying clustering or some of the classification is understanding, what is a true positive, meaning you have cancer and I predicted you have cancer. I got that spot on. Well, what happens in the false negative where I say you don't have cancer, but you actually did have cancer? That's not a good situation. And likewise, if you don't have cancer and I tell you have cancer, that's equally not good. And that's why you see those two red things, they're called out. And this is a perfect example of that, of both the false positive and false negative. Is your doctor tells you that you're pregnant and you're a dude, you're going to be like, what? And then, you're 9 months pregnant and she's saying, sorry, you're not pregnant. That's the severity of these false positive, false negatives.
Okay.
And
that's a great analogy.
I can't take credit from this. I saw this at Brooke Weir did this for us at the Databricks training, and I thought it was a brilliant slide. Brilliant representation. But it is so true, and this is going back to the importance of these evaluation metrics, especially as you're telling your story, and if there are data scientists in the room, it's so important to carry through evaluation into the story you share for this exact reason, because that's going to be the very first question that anyone in the room who even knows a tiny bit about just statistics in general, not even machine learning, is going to ask. And Azure does a great job of providing that for you. If we're talking about Studio, once you drag on that evaluate your model, tile, and you connect it to your test tile in the drag and drop GUI, it's done for you. All of that hard work and all of these, metrics are already provided. So you don't even have to think about it. And that's one of those great things Azure does for helping that data science process along.
Very cool. Yeah, well, I feel definitely much smarter than I was at the beginning. So, yeah.
And we are at our last few slides here, but I just wanted to show you my favorite model because I find that it's so applicable in so many different scenarios. So I'm a big fan of neural network, but of course, there's this perfect analogy where if you ask a data scientist how much 1 + 1 is, I'm going to go into this complex explanation of, well, first I need to measure how solid that 1 is and what decimal point precision is it? Is it really 1 or is it rounded to 1? Whereas you ask somebody else and they're going to say 2, so. Yeah. For me, decision tree is one of these perfect blends between what you get in the complexity of a neural network with still getting that whole interactive multifactorial that we talked about in your genomics example. So if you imagine each of those blue areas are that, decision point that can help you trigger one way or the other. Is there anatomy this or that? Is there gene structure this or that? And this can be as deep or have as many leaves as a normal tree. So if you think about a tree with branches and you think about looking at the overarching tree, That tree is the final accepting of the offer. Should I accept this new job offer? That's your why. And so now you need to predict, what are the variables that make me change my mind if I'm going to accept a job? Well, one of the first things you probably look at, so that base node is, what's the salary? Is it high or is it low? And sometimes there may even be another branch off of that, which is your counteroffer. So even if it is a no, you don't like the salary, well, then you could then offer up something else to them. So these branches can branch off each other, much like a tree does. But if you answer yes, then you go into each of the different decision nodes that might affect your the thing you're trying to predict. In this instance, should I take this job offer? And so I love this sort of analogy because it's, if you think about what your brain does as you're sorting through, do I take this job? This is very much what you think through. What are the benefits? What's the salary? Is it a long commute? I don't really think about coffee because I gave up caffeine, if you can believe it. But you do think, you think about these factors to come up with whether you decline something or accept something. And that's where a decision tree is so applicable in so many different business cases to answer those factors. And best yet, then you actually get to understand those blue decision points. You actually get to understand the correlation between them. Is commute and salary related? Do they have a high correlation? Is salary and coffee, do they have a high correlation? And so you start to understand which of those features are most significant to moving that needle of accepting that offer. So my favorite algorithm, I highly recommend using decision trees. Secret.
That's great.
So did you use this in accepting your job here?
Funnily enough, I did. I was at a fish store, and I ran through, well, the salary isn't this, but the benefits are that, and ooh, there's ESPP, and yes. So by the end, I accepted the offer and bought a fish and an anemone. Ooh, that's hard to say. And so we're coming to our last examples here, and I just wanted, the second most common thing I get asked to come in and talk about at many of our customers is this concept of recommenders. And so a recommendation system is just like you probably have experience with if you go to Amazon and that concept of your gold box offers they used to have, or customers who bought this also like that. These are all recommendation systems. The Netflix movies that they show up, recommendation systems. And if you think about, maybe 5 years ago, if you were using Amazon, I can tell you that these systems were not that smart because I would buy my husband maybe some tools. And every recommendation that came after that would be related to tools. Husqvarna, you want a chainsaw, Laura. And I'm like, no, I don't. You should know because I marked a gift that this is not for me.
Yeah.
But it didn't. And that's where over time, as computation power has become so much greater, that we've been able to hone these models and really get better. Now Amazon knows when I buy a gift that it's probably not something I like. Or maybe it is. Maybe they've seen a pattern on the things I buy myself are the same things I buy as gifts for others. My Netflix queue is the same way. If my son goes in there and forgets to change to his, suddenly now I'm watching Llama Llama and all the cartoons he watches instead of my much darker Netflix choices.
There's nothing wrong with Llama Llama. I just want to tell you that right now.
I have to say Llama Llama Mama Drama is my favorite just because it's fun to say. So recommendation systems are super powerful. Even, I'm a gamer, and I always wondered, how does Xbox Live come up with this list of people that I could play with or that they recommend to me, or even the free gold, games that I should play or download for this month? All of that's based on recommendation systems of other users that are similar to me, that have similar gameplay style. And so if you think about the lesson I've given you today, what do you think, or which model do you think can help facilitate these recommendation systems, knowing what my preferences are based on others?
Decision tree?
Very good. Very good. That is exactly right. You get a gold star.
Yay!
So there's a decision point that goes through here where it says, is this profile Laura's or her family's? It's Laura's. Okay. Is it in her list already that she wants to see, or is it something that's similar to her list? Okay, yes or no. And it goes through that process, and when it gets to the end, it makes those recommendations for you. And so everything that we do in the web today, in social media, in advertising, in our searching, all has recommendation systems behind it. Because if we didn't have recommendation system, we would have non-optimized Husqvarna chainsaws plaguing our view and skewing our ability to buy what we were looking to buy or search for what we were looking to search. These are very powerful systems. Do you guys have a lot of experience with them in your customers or asks for them?
Oh, every day. It seems like every day, there's some type of, I know just personally, when I'm listening through music, Spotify wants to give me, my Discover Weekly. And so, at first it was kind of a hit and miss, but it's gotten a lot better to the genres of music that I like. So I have to say, yeah. But then it gets to be an annoyance sometimes.
It does.
I just happen to one time now search on maybe a Facebook page or a Twitter page, and then everywhere I go, it's filled in on the side channels, with recommendations.
Yeah. I noticed that some of those cookie-based tracking mechanisms aren't very intelligent in terms of recommendations, probably because they don't have a lot of other history to go along with it, other than you click on this link.
Absolutely.
Right.
Yeah, it is really annoying. I once was dreaming about Bora Bora, and I now am plagued by Bora Bora, like vacation things popping up everywhere. And while it's lovely to look at, it's like, oh, okay, go away. Airbnb is notorious for that, where it's like, I only searched for it once. Leave me alone.
Yeah.
Similarly, there is the content-based approach. So while we were talking about the recommenders here that are based off of you explicitly searching, which again is more of a supervised learning model because you're explicitly typing into Google the labels of what you're searching for. There's also this content-based approach whereby you know that you like a certain item because you buy it. So you think about Publix or any grocery store. And therefore, similar items that are maybe branded in the same way, you could potentially like. I mean, my husband wears shirts that are branded with everything from, of course, Microsoft because he's a loyalist.
Oh, but perfect.
To any time there's a free shirt, he seems to then start gravitating towards buying the product. It's weird the way our brains work, but that's very much our brain acting as a machine on the content-based approach.
Yeah.
And this is why commercials are so effective at getting us to buy stuff. And so there's also this concept to be wary of in doing it with when we're looking at these models and extrapolating. So extrapolating occurs in everything we do. We extrapolate personally. So I come home, I see, one dog is, had an accident on the floor, and I extrapolate out that now it's just a mess. Now everything, I need to have my carpets cleaned, and I go through all this rigmarole because of this one accident, and that's just because I have extrapolated out what that means in the long term to my carpet. I prefer being clean. But if this is a great sort of analogy of looking at, if we were looking between a person's number of husbands over time, if you were to extrapolate, between the time frame of a normal lifetime, most people might have 1 million husbands by the time of their lifetime if they were to get married on a daily basis. But the point being is that some people only marry once in their lifetime. There's not a relationship between time and number of husbands. And so it's very important to make sure when you're going through and analyzing your result set that you don't come any preconceived notions and you don't extrapolate out what the meaning. I'm sure you've heard them say correlation is not causation. And
Absolutely.
This is very true.
Yep. Good point.
This goes back to your earlier point about understanding what your data means, and predicting your life expectancy if within 2,000 years or the life expectancy of a car. Yeah. Okay.
No, it's very true. And I'm getting caught all the time when I look at something that seems to have a causal result, and I have to remind myself that just because I see the correlative result does not mean it's causary.
Interesting.
And so, reinforcement learning just, makes me laugh because this is really the key of what I'd love to come back and show sometime if you guys invite me is my famous fantasy football model that I know everyone's like, what? I know I've heard so much about it. Why won't she pipe down about her fantasy football model? But it's a perfect example of reinforcement learning because I was told by my father-in-law that statistics could never predict fantasy football, and I knew zero about professional football at the time, and this was 5 years ago. And I took that on as a challenge, like, oh, yeah, old man, I'm going to show you. And lo and behold, I failed miserably year one, and that's because I didn't have enough time to train. Mm-hmm. Plus, that experience was really that negative reinforcement where I knew the positive result I wanted, which was winning, but I didn't achieve it that year. I knew I was going to come back the next year stronger with better and different inputs and features. And I started pulling in everything I could. And it's really a great sort of example of reinforced learning. I learned from my failure and I moved on. And then the next second, third, fourth, fifth year, I've won my fantasy league. And then, that to me is a great example of making him, well, he still hasn't bowed down to my power of my statistical learning, but maybe one day. But still, it's a great example of taking a machine learning world and applying it to everything from like in a poker game even, or counting cards, not that we do that ever, but in blackjack. These things are all things
illegal.
It is technically, that's what I mean. It is illegal.
We're crossing the gray line here, people.
But if you think about just gameplay in general, there's a reinforcement of positivity by winning, and then there's a negativity of losing. And that's all what reinforced learning is, and it's the ability to have a set of positive outcomes, negative outcomes that change behavior. Purely Pavlovian. If I forget to feed my dog's going to cry for me. Actually, it's the reverse Pavlovian on me. And wait. So, when they start, even if it's the middle of the night, I will jet up out of bed like, oh, you need food? You need water? What do you need? Totally reverse Pavlov, but it works.
We might be able to help you with that.
I know. I've told this story, and they're like, the word no comes to mind.
Right.
Well, very cool.
And this is the last slide here, and this goes back to just remembering that when we're making these overly investigative remarks and people say to you, we know what causes the outcomes of this, you just have to remember that there's no link between many things. Even if people believe there's a link, oftentimes we're going to find there's not. And no matter how many times they want you to investigate it, it's just not. So what I do is I listen, I consume it, and I'll use whatever that is that they believe the link is caused from, but I will make sure to bring in every other potential feature and let the machine learning model tell me what actually is causing whatever the event may be.
Oh, that is awesome.
Yeah. Thank you very much for kind of breaking that down. I think we definitely should have you back, and I'd like to see more of how you actually assembled your machine learning model for your fantasy league.
I will definitely do that.
Is it for sale? That's what I want to know.
I know. I am, and it's funny. It's using what's called a multi-arm bandit algorithm, which it just makes me laugh. And it goes after the slot machine concept of the arm to look at, am I going to win this week versus this person I'm playing against, much like, am I going to flip over tiles in a slot machine that are going to achieve a win? And so, I would love to walk you through that. I think, not to pat myself on the back, but I think it's a unique way to approach it. Plus, I scrape social data because I made the assumption that I validated that people who have events going on in social media, positive and negative, influence gameplay. And sure enough, it turns out that is the case. So I'd love to show you.
Oh, that is too cool.
Wow. Yeah, I've actually, now that you mentioned that, there's made me think of some customers that I've been working with who try to mine, particularly ones that are very public and prominent, who have active social media channels where they mine those sorts of customer feedback mechanisms and try to detect what customer sentiment is. And
absolutely.
Yeah.
And sentiment involves so much. A lot of times people will go through sentiment and not realize just how much actually needs to be involved in sentiment. And that's why it's so important when you're looking at sort of those sources and crisply defining that problem like sentiment is to pull in not just sentiment, but also look at things like what are their transactions, because a customer may tell you in sentiment that they're happy. This is why surveys can be very ineffective. Most people don't want to share bad news, and most people are sort of blandish neutral. They're never super happy and they're never super upset. They're somewhere in the middle. But when you start to tie together survey scoring and or sentiment, what they say in tweets or in social media with their transactions, now you know intent. So even if they aren't happy but they're still buying from you, then you can make the judgment call over whether or not that's a really important thing to tackle versus those who, aren't buying from you anymore and were unhappy. Maybe those are the people you want to go after.
Interesting.
And just to wrap this down, I just wanted to show you a quick model in terms of Azure's world of looking at exactly what we just talked about. So the business value side on the right is really that why, that question. What are you answering? That's what you want to visualize. You want to take that, sales number. You want to take that outcomes. That's what you want to put on these dashboards or reports that you're providing. The business problem on the far left then becomes that source of data, that spreadsheet of columns with your first column being that Y number that you're trying to predict and every other column being those features. And, wherever that's stored, it's sort of 6 of one, half a dozen of another in terms of machine learning. And then in the middle is where sort of the power of, whether you're using ML Studio or Workbench, again, those are desktop tools. That's a choice and a preference. Are you the citizen data scientist, or are you the one who's going to get in there and script write in Python and R? And then, from there, it's where you then start pushing these out and operationalizing them. From my opinion, Azure makes that operationalizing so easy, that model management, the things that typically have been so difficult as a data scientist to compare models to one another. That's where Azure's strength really lies, is in simplifying that.
Well, the name of the show, Cloud Simplified, so let's see what we can do to simplify this for our viewers farther in a future episode.
Yep. Hey, Laura, really appreciate you sharing with us today, and we're looking forward to hearing more in another episode at some point. Absolutely.
Thank you.